Greeting, ladies and gentlemen. Today video we're gonna answering question number 10. The composite shaft shown consists of 5mm thick brace jacket that have a modulus of rigidity for brace 39 gigapascal, bone to E 14mm diameter of steel core, which G is still 77.2 gigapascal. Knowing that the shaft is subjected to E 600 Nm torque, determine the maximum shearing stress in the brace jacket. B, the maximum shearing stress in the steel core. And in C, the angle of twist of B relative to A. So answering 75.45 megapascal. There is the reference answer. But anyway, we have a rod that made from the composite shaft. That is composite shaft made of brace, combination of brace and steel. For the core, it will be steel, and for the outer, there will be brace. So we have that composite shaft. We exerted a torque. If you took point of view right here, there is a torque from that point A, and there is an internal torque from the applied torque. So you will have the steel have a diameter about 40mm, and for the brace, it being stated, you will have 5mm thick brace jacket. But anyway, let's go through to the problem solving. First thing first, you need to done the FBD. I make an analysis. For the first one, it will be analysis of a brace. If you take a look in the front view from this side, you will see there is a torque exerted upward for the applied torque, and there is an internal torque that apply in different direction but in the same magnitude. Question asking what is the shearing stress for the brace and for the steel. So there is the question. While I'm answering this question, since that the question number 10 is similar as question number 9, I make a similar reference, and there is the relationship that I get, which is internal torque for the brace plus by internal torque for the steel equal to 600 Nm. So this means, if attempt to answering this question, we will use elastic torsion formula. Tau maximum refer to shearing stress, which is what is the question asking, equal to internal torque for B, since that we were making an analysis at brace, C maximum over by JB. Internal torque for B, we cannot just slightly taking 600 Nm, because this equation is saying that for internal torque for B, it will be lower than 600 Nm, so the value will be different. So you cannot just take it slightly 600 Nm into the account. So I don't know, until now I'm still thinking why this question is legit. But anyway, when C max, since that we were dealing with for the first analysis, there will be brace. So if you take a look for the brace cross section, it is a hollow shaft. You will have an outer diameter and inner diameter. Inner diameter will bring you the minimum shearing stress, and the outer diameter that will bring you maximum shearing stress. So that's why the value of C max in here, that will be equal to radius, outer radius for the brace, equal to 0.025 meter. It's come from if you take a look from the equation, the diameter for the steel core, that will be 40mm, and you will have another layer, and this layer have a thickness about 5mm. So when we're talking about the the outer radius for the brace, point of analysis is from the origin into there. So this means you need to divide 14 by 2, you will get 20. Then you need to plus it by 5. So that you will get the outer radius for the brace. So that's why you will get 0.020 meter. You will get 20 millimeter, but you need to change it into meter because we were dealing with a modulus of rigidity. We were dealing with a torque in the form of SI unit. So any kind of length, any existing of length, you need to make sure it is in meter. But anyway, 0.025 right there, meter. So modulus of rigidity for the hollow shaft, there will be this equation equal to pi over by 2 c the power of 4 outer radius minus by inner radius the power of 4. So the outer radius will be 0.025 meter. The inner radius there will be just simply as 40 millimeter divided by 2. Convert into meter, you will get 0.02 meter. So this is the modulus of rigidity for brace. Now, since that mathematically we cannot solve this equation because we have two unknown, which is internal torque for brace, we don't know, and the shearing stress for brace, we don't know. Of course, it is what question asking. So you have two unknown, mathematically you cannot solve that. So we need another relationship. Now, there is the logic for the second relationship. For the third, to be honest, equation. It been stated that the brace and steel were bound together. If they were joined together and there is no slip while this object were exerted by a torque, it is mean if brace were rotating by 4 degree, then it's just logic to say if there is no slip while the process will happen, the steel also will be twisted by 4 degree. So that's why in here you will state that whatever angle of twist for brace, it will be the angle of twist for the steel. They will share the same magnitude of angle of twist. So that's why angle of twist phi B equal to phi S. Angle of twist at brace equal to angle of twist for steel. So there is another equation that we will use. Angle of twist of phi equal to length times by internal torque over by the polar moment of inertia times by modulus of rigidity. So that is the formula that we were using. So now, this is the third equation. The first equation will be this one. The second will be this one. And it is the third equation. So now, we're trying to solve this equation. Is that the core equation will be this one. We want to find out the internal torque for B. And it is there is a unknown for B right here. So maybe we can solve this equation. Maybe we can solve the internal torque for brace from here, so that we can solve the core equation and get the answer. So anyway, LB and LS, there will be 2 meter. Internal torque for B, we don't know. Internal torque for S, we don't know. So polar moment of inertia for brace, there will be this one. Polar moment of inertia for steel, we not calculate yet. The modulus of rigidity for brace, there will be 39 gigapascal. And for the steel, that will be 77.2 gigapascal, which is being written in the question above. So anyway, we need to find out the polar moment of inertia for steel. There is the formula, since that the shape for steel, there will be in the rod solid shaft. So the polar moment will be pi over by 2 c the power of 4. And the radius for steel, there will be 40 millimeter divided by 2, convert into meter, you will get 0.02 meter. So you power it by 4, you will get 2.51 times by 10 to the power of -7. So you know what is the polar moment of inertia for steel. You can include that value in here, and all of these value that you know in this equation, you simplify it even more. you will get this relationship, which is internal torque for brace equal to internal torque for the steel times by 0.7 to 9. Now, we can relate this equation with the first equation that we have. Internal torque for B plus by internal torque for S equal to 600 Nm, which is it had been written, we write above right here. So we transfer the value for internal torque steel to the other side. You will get internal torque for brace equal to 600 minus by internal torque for steel. So you include the data, the internal torque for brace in the upper equation. You will get internal torque for S or steel equal to 347.02 Nm. So there is the value for internal torque for this steel. According to the core equation, we make an analysis for brace. We need to find out what is the internal torque for brace. So we can just include the internal torque for steel in here and find the internal torque for brace, which is right here, 600 minus by 347.02. You will get internal torque for brace. You times it by the 0.025, the value of outer radius, and polar moment of inertia for brace, there will be 3.623 times by 10 to the power of negative 7. Thus, you will get shear stress for brace will be 17.46 megapascal, which is in here, 70.45 megapascal. So you were using the elastic torsion formula yet again, and you include the data, which is tau internal torque for steel. There will be 347.02, which is had been calculated before. The C max, there will be 0.02 meter. The radius for the steel, there will be 0.02 meter. Polar moment of inertia of it, which is where is it? This one, 2.51 times by 10 to the power negative 7. Then you do the math, you will get 27.7 megapascal. So there is the shearing stress for the steel. Now, angle of twist. Since that angle of twist for brace and steel will share the same magnitude, it doesn't matter. We didn't want to make an analysis for brace or steel. It just come out with the same magnitude. So in here, I make an analysis for brace. Since that angle of twist for brace equal to angle of twist for steel, I make an analysis for brace. We were using this equation, length B times by internal torque for B over by the polar moment of inertia for B times by its modulus of rigidity. So the polar moment of inertia 3.623 times by 10 to the power negative 7, modulus of rigidity 39 gigapascal, and the internal torque that will be 2.98. It is just simply as 600 minus by 347.02, you will get 252.98 if not mistaken. Then you calculate, you will get the angle of twist in radius in rate, which is 0.036 in rate. Then you convert it into meter, you will get approximately to 2.05 degree. Maybe, oh yes, it is that number right there. There is that answer. How do you want to convert the rate into degree? It's just simply as times it by times 0.0336 by 118 degree over by pi. So you will get 2.05 degree. So I think that's all for this question. It has been at 12:16 AM. It's already 12:16 AM. I need to stop here since the lecture is over. I want to continue watching the crash on you since from the drama. I'll wait under the tree waiting for the maid to come down. So I think that's all for today. Thank you for watching and have a nice day. Bye bye.